All right, so one thing that we're going to go over before we jump into the graphing part is how to find the arc length of a circle. So let's say this is our circle. Here's the center. If I have some random angle theta, okay, let's see. What do we know about the total number of radians in the entire circle? How many radians is it? 2 pi, okay? So the total is 2 pi, and this angle theta is a fraction of that circle, right? And what do we know about the circumference of the circle? What's the equation for circumference?
Pi over 2, or like the 2 pi r.
Yeah, 2 pi r. So circumference is 2 pi r, and then we're trying to find this arc length. And arc length is basically the length of the circle in between 2 points. And so we're going to call this S. Okay, so this S is also a fraction of this entire circumference, right? So we're going to say S over 2 pi r. And since this is pretty much like it's one angle that's intersecting the circle over there, we're going to say that these two things are equal to each other because they're going to be proportional, right? This piece is a fraction of the whole circle, just like this angle is a fraction of this whole circle. Okay?
What is the numerator of the thing above 2 pi?
Yes, theta.
Theta.
Yeah.
Okay.
Yeah, Aaron and I might write it a little bit differently, but yeah, theta is just this, looks like a 0 and has a line in the middle. And that's the Greek letter for what we use for angles. So if we set these equal to each other and we multiply both sides by 2 pi, then we get theta equals S over R. So S equals R theta. Okay? And this is the equation that you can use to find the arc length of any circle given R. This is the radius. And this is the angle. So as long as you know the radius and the angle that is intersecting the circle, you can find the arc length using this equation. So we did, here is where we took care of the angle, and I'm using radians instead of degrees. So instead of 360, if you wanted to do 360, it would pretty much be the same thing. We're just using proportions. But now that we have radians, it's really convenient because 2 pi r is the equation for circumference, and 2 pi is the total angle measure of the circle. So those can just cancel out. That's why I used radians instead.
So your final answer will be in units of radians?
Yes, it'll be units of radians. And in general, just so we kind of know like what this formatting stuff is, if you just write like theta equals 1 without any units, this means it's 1 radian. And if you want to say it's 1 degree, then you have to put a degree sign. But if you don't put anything there at all, like if you just say theta equals pi, that automatically means it's pi radians, not pi degrees. Got it? Okay, so now let's jump into graphing. So let's start with y equals sine of x. And that will look like this. And let's change this so that it's a little easier to see. Let's make that pi. So essentially when you're graphing a trig function, so let's put the unit circle back. Well, I'll just refer to that one tonight. So just like any function, we're just graphing the y values as we go x, and as we go along the x-axis in terms of x. But in this case, x is a measure of the angle that you're rotating. So x, if x is pi, then you can think of if in the unit circle, then x would be let's say x is pi over 2, then this would be pi over 2, and then your y value for sine of x would be 1, right? Because the unit circle, it's kind of hard to see. But so that's essentially what we're doing. And you can think of it also in terms of a table. So if we had x and y, and then we had like 0 and pi over 4 and pi over 2. You're basically finding sine of x and putting it in this y column. And when you graph that, you'll get this wave, this cool wave like function that every, like, I don't know if you guys have learned about waves in chemistry, but like the components repeat itself every period. So every certain amount of time, they repeat themselves. And that's because as you're going around the circle, as your angle x gets bigger and bigger, bigger, eventually it'll come back here and it'll do the same thing over and over and over again, right? It'll just keep going around the circle, and then your y values will just repeat and repeat. So your parent function for sine x looks like this. A couple things to notice is that it passes straight through the origin, and if we write the parent equation as y equals a sine bx c plus d. All these variables, a, b, c, d, we've already worked with this kind of stuff. It's just transformations. That's the only thing we're doing. But in this case, we can use these, we can like evaluate these transformations in terms of the period and the amplitude, which I'll talk about in a second, and they'll help you graph things. So instead of, when we're transforming this, instead of talking about like vertical stretches and like horizontal stretches and stuff, we're going to talk about like the period length and the amplitude and things like that. So A up here, this represents the amplitude. The absolute value of A is going to be the amplitude. And essentially what that is it's the distance from that middle of the wave to the crest or to the trough. That should be A and that should be A. Now if A was negative and it was a sine wave, then it would go like this, but it would still be the same thing because it's the absolute value of A.
Wait, it's the distance from what to what?
From this middle of the graph. So if you were to chop it directly in half so that there's like an equal part on top and an equal part on the bottom, and then you take the distance from this middle piece all the way to the top here or to the bottom there, this distance, that would be A. That's the amplitude. And the amplitude is a measure of the vertical stretch. But again, we're not going to talk about it in terms of vertical stretch. We're going to talk about it in terms of amplitude. So if I put a 2 in front of here, that means A equals 2. You can see that the amplitude increases from 1 to 2 because now A is 2, right? And if this was 3, then it would increase to 3. See that? Okay. This letter B is going to help you find the period. For any sine function, the period is going to be 2 pi over b. 2 pi over b. Okay? And b, if we're thinking about it in terms of the transformations we've been doing, it's a horizontal stretch and compression factor, but we're thinking of it in terms of the period right now. So the period is basically the distance between corresponding parts of the wave. So it goes through one cycle here, and then afterwards it just repeats it again. That's another cycle. This part is exactly the same as that, right? So we're just going to call this whole chunk here, this is one period, this length.
And what does that represent?
This is sort of the same thing as a horizontal or...
No, but like on the equation.
But I don't really understand your question.
Like in terms of like the actual equation, what would the distance between like the period represent?
Well, you would take this into account when you're graphing, because if we go back to just sine of x, so the period is basically the distance between any corresponding point. So as long as you know how long one cycle is, then you can repeat that for however many times, right? So the period, I guess it's essentially telling you how long this one cycle is going to be. Is it going to start here and go there? So if I put a 2 over here, notice how everything gets squished this way? because the period would now be 2 pi over 2, which is pi, right, instead of 2 pi, which means that one cycle of the graph, so one wave like this, instead of going all the way from here, it would just be covering this little bit because the period just got shorter.
And the two pi over b that was we looked at earlier, what does that represent?
That represents the period length. So if you're given this equation, in order to find the length of the period, you would do 2 pi over b. Okay, and then C and D are horizontal and vertical translations. So they're not stretching the graph or anything. They're just moving it around. So if I were to add 1 to this, it would move it up 1. And notice that the point that used to be at the origin, this used to be at 0, 0. Now it's at 0, 1 because it's been moved up. And notice that the amplitude, what's the amplitude of this graph? What's A? 1, right? So the highest point on the graph is just going to go 1 up from here and 1 down from here. And it doesn't matter how far up we move it, we go all the way up there. Then since we know the amplitude, we know that the highest and lowest points are going to be 1 up from there and 1 down from there. Kind of makes sense? Right, this does not represent amplitude. This one does.
Oh, that one?
This is amplitude.
Oh, so you don't multiply it. Like, you multiply, like, you multiply A to the equation.
What do you mean? Like, is A multiplied by all that? Yeah.
Oh.
Yeah. So it would be like 2 sine of x or something. In that case, the amplitude would be 2 because the distance from here to up there, this is 2. And then the plus d part is just moving it up and down. So we just moved it up a little bit. Okay, so that is sine graphs. I'm just trying to get out. Okay. So why don't you guys try a few of these?
One more question.
Yeah.
So for the periods and the period lengths, are these exclusive to sine functions, or can these be like these definitions be used for all the functions?
The sine, the period thing, the 2 pi over b, that's for both sine and cosine. And the reason that is because if you have a circle, and then you're like, x is your angle, and you're going around and around and around, right? After x reaches 2 pi, then it will have completed one cycle if you don't transform it at all. But if you're horizontally like compressing or stretching it, then it might take like, instead of x, maybe your angle would become half x, and then it would take twice as long for you to get all the way around, and that's why your period would become longer. Or this would become like 2x, and then it would take half as long, and so the period would become shorter. And so that's why for sine and cosine, it works to do the 2 pi over b. For tangent and cotangent, we'll go over that in a second, but it's slightly different for that one. And that's because tangent repeats differently from sine and cosine. So let's do a practice problem. Let's do y equals sine of 2x plus, well, let's just do a bunch of simple ones. Sine of 2x. And
What do you want us to do with these?
graph them. I'd like you to graph them.
Like by hand?
Yes, by hand. And when you're done, put your pencil down so I know you're ready. Has anyone finished the first one? Almost.
Is it okay if you get like a bunch of like really like tiny points?
Oh, what do you mean?
Like I'm getting like really small numbers, like when I'm plotting them, that's fine.
Right. So yes, that should be what you're getting because what's the amplitude on this graph?
1.
Right. So basically the graph is going to stay between -1 and 1.
Okay, I see.
Right. But why don't we go over the first one together because we can do this without having to plot many points. Okay. So can someone tell me what the amplitude? We already said this, but what's the amplitude of this? 1. What's the period?
Pi.
Pi. Okay. So
What's this period?
the period is the length of one cycle. So it would, if we look at this graph, the period would be from like this point here to that point there. It's just one cycle. Or it could be from here to there, depending on whatever points you want to choose. But it's the distance between corresponding points on the graph. For sine, I usually like to use the ones that are kind of on the same line as this middle point right here. And this middle point is really useful for keeping track of where the graph is moving along. So first, we're going to label the x-axis in terms of pi, like it is down here. We're not going to evaluate pi. We're not going to say, oh, pi over 3 is like 1 point something. We're just going to leave it in terms of pi. And so we know that the period is 2, and the amplitude is 1. So we can label it 1 up there and -1 down there because the graph is going to be staying between those two. And usually we just want to graph 1 or 2 periods of this, and then we'll get a sense of what the entire thing will look like. So we know this has not been moved left or right at all, right? So we know that it goes through the origin, right? And since the period is 2, notice that, let me just graph sine x.
Wait, isn't the period?
I mean, yeah, sorry, the period is pi. My bad. If you divide, notice that this graph has like, it looks like it has 2 chunks, one that goes under and one that goes over, right? And this whole length from here to here, that's the period. So this length here is half of the period, and this length here is half of the period, right? And then if we go halfway between this half, right over here, that's where one of our minimums is, right? And so this is a quarter of the period, this is a quarter of the period, right? So we know that our total period is going to be pi. So which means half of the period is going to be pi over 2. Okay, so I'm going to put pi over 2 over here. And the other half is going to go another pi over 2 in the other direction. Negative pi over 2, right? And then halfway between this middle point and the end of the cycle, what's pi over 2 divided by 2?
Pi
over 4. Yeah. That's going to be pi over 4. Okay, and then this one is going to be negative pi over 4. Okay, so we know that there is going to be a maximum at pi over 4 and a minimum at negative pi over 4, and then it's going to come back here at these 2 points. Am I going too fast? Does this make sense? And then we can connect these like so.
So
Okay.
there's a minimum at pi over.
Right. Pi over 4 and negative pi over 4.
This is the parent function.
No, this is not. The parent function is sine x. This is sine of 2x. So our period of the parent function, sorry, this is pi, my bad. The period of the parent function would be 2 pi. Because the parent function is y equals sine x, and then b equals 1, right? So period equals 2 pi over 1, which is 2 pi. In this case, we had a 2 there. And if you think of this in terms of horizontal compressions and stretches, this is the same thing as 1 over half, right? So it's the same thing as a horizontal compression times a factor of 2, or half. And so that's why it's been shrunk this way. And so if we add a 2 right here, we can see that sine 2x. So you can see that in the parent function, which is blue, the period is from negative pi to pi. So the whole thing is 2 pi, right? And in this second one where we added a 2 here, the period is now half of that. It's been squished this way. Got it?
So for if it was sin 3x, then it'd be pi over 3, like pi over 3, or like the 2, like the standard.
Well, let's do that one. Sine of 3x. So the period would be
2 over 3 pi.
yeah, 2 pi over 3. And then you divide that by 2. Yeah, right.
Oh, pi.
Yep, so then it would be pi over 3 this way and pi over 3 that way. Okay? And so this can get a little bit wonky once you start moving it left, right, up, down. But just keep track of where this middle point is and how far the period is on either side. Keep track of, like, it comes back to exactly where it was half the cycle here, after half of the period, and then half the period that way. So that's just something to keep track of. And let's move on to the second one. Do you want to go over this together, or has anyone finished it, or
Oh, no.
do you want to go over it together, or you want to do it yourself?
Sure. Whatever.
Okay, let's go over this one together, and then you guys can do the last one yourselves. So what is the period here? 2 pi. That's correct. Yeah, be careful. It's 2 pi over b,
Oh,
not just pi. So period is going to be 2 pi. What's the amplitude?
2.
2. We good, Kristen?
Why is the period 2?
Period is 2 pi because b is 1, and you find the period by doing 2 pi over b, right? Okay, so the period is going to be 2 pi. So I'm just going to graph it on top of this one so we can kind of see the difference between the two graphs. So how far this way is my first cycle going to go? Or the half of my first cycle going to go? Pi, right? You divide that by 2, so you know you're going to go pi that way. Okay, and you know there's going to be a point there. And how far this way? Negative pi. Okay, and then where are my maxima and minima going to be?
2.
Oh, the y values, yes. That makes sense. But where on the x coordinates are they going to be?
Pi over 2.
Pi over 2 and negative pi over 2, exactly. Just halfway between these. Okay, so we're going to go up here. There's one point there, and there's another point there.
So the maxima and minima on the x-axis is just half of the period?
It's half of the half, so it's a
Half
quarter
of
of
the-
it.
okay,
Yeah.
quarter of
So
the
this is, right. Okay, and then you connect these points. There you go. And right now I'm just graphing one period of the function. So if I was to graph like a second period, then I'd go like off that way or something. And if they say only graph one period, then you can leave these circles just as they are. But if they say to like graph the function in general, that means it's going to continue on forever in either direction, right? So then you've got to include these arrows. It's going to continue either way. Okay? Do you guys want to try this one? It's a little bit tricky. There is a horizontal translation. So when you guys try it,
Is that 2x minus n or 2x minus
pi,
pi?
sorry. Pi. I'll be right back.
1. Okay.
Just a hint, as you guys are working, keep track of this middle point. Whenever this moves it left or right, keep track of the middle point, and then just do exactly what we've been doing.
Is it okay to round in these cases, or like, do you want to keep it as a fraction?
What do you mean?
Like for finding the period, it's like 2 pi over 2x minus pi.
The period is just 2 pi over b,
And b is?
and b is just the coefficient of x.
Oh, just the coefficient.
Yeah, so it's not going to be, oh, I see what you're,
Yeah.
yeah, I see what that wasn't clear. Yeah, so b is just the coefficient of x, just like if you're doing a horizontal stretch or horizontal compression, you would just multiply x by some number. That number is b.
So the coefficient is just 2,
Yes.
so 2 pi over 2.
Yeah. Are you done?
Yeah.
Do you want to come up and draw it? There's space. The other way, so it's stuff.
Oops.
See?
Can I have a marker that works? You were using one. Right?
All of these should work.
Yeah, this one's.
Okay, cool. Oh, yeah, that was dead. Let's see. The only thing is these that's pretty triangular, but as long as you make it like a little curvy. No, actually, there's one thing. Let me see that. So what's the period on the graph we just drew? Is it? So how many cycles did you draw? Just drew one cycle, right? So from here to there, that would be one period. That's too high, right? So you can just change the numbers down there, it'll be fine. Where is this? Oh, this is under pi over 4. Oh, so this is supposed to be the origin. So your graph looks like that?
Yeah.
Okay. Fine. Here's an item. Got it? So, Kristen, does your graph look the same as this one? Yours looks like this, huh? Like this? Yeah, so it's basically the same thing. He just drew this part, this like chunk of it, and drew the arrows, and you just drew the other chunk. And both of them are correct. So I'm going to use both of yours as examples. When I look at this, I can think of this in one of two ways. So, oh, this one's time. Or whatever. So, I know that the period is pi. You made the same mistake as me. I did the same thing. So the period is pi, right? And amplitude is 1. Yeah. Okay. So we know that the period is pi, and we know that every single period is the same, right? So if you move this right to the right pi, then it's just going to be shifted that way. And pi, so period is pi. Maybe I'll show you what it does this here. Period equals pi, and you're moving it right, pi. Okay? So if this was a random sine function, basically we're saying that this is pi, and here's pi, and also from here to here is pi, and also from here to here is pi, So if you move this to the right pi, you're just going to be moving it over and it'll look exactly the same because this cycle is exactly the same as that one, is exactly the same as that one, right? You can see that on Desmos. Okay, let's just do sine 2x. And then 2x minus pi. Oopsie. I messed something up. Where did I mess up? I just did something wonky. Hold on. That's fine. Three, 5. Okay, I don't know what I'm doing weird here on Desmos, but I'll try again. Oh, okay. I see where we all messed up. I made the exact same mistake. Okay, everybody's wrong. Well, I made the same mistake though, so it's fine. Actually, it's not fine, but okay. So here's where we messed up. What's the order of transformations? We've been doing this for the entire summer and we've all messed up on this. What's the order of transformations here? Yeah, so this is the same thing as sine 2 x minus pi over 2. Right? So our period's still 2, that's still correct. But our horizontal translation is not quite right because we can't just look at this and say, oh yeah, it's moved right to the right pi. No, it was actually moved to the right by that much. Or you could think of it as it was moved to the right and then it was compressed. So let's all walk through this together since we all made the same mistake. And then we can move on to cosines. Okay. So if we look at this graph, first we moved it right by pi units. And then we horizontally compress by factor of half. Okay, and this is what's going to affect the period. So the important thing to note is that you have to move it right first and then deal with the period. So the parent function would be like this. Right? And then if we move this to the right pi, it'll look like that. Right? And then we'll deal with the period. So now we know that instead of the period being all the way out here, 2 pi, now we know that the period has been squashed, right? And now the period is what? 2 pi over 2, which is pi. And then we know that this is pi over 2, this is pi over 2. Okay, and then it'll look like that. That's where all of us messed up, including me. So this is a really easy mistake to make. Just important to remember this order of stuff. Okay, so that is what your final graph should look like. And I apologize for saying you were right when you weren't. Okay. Are we all comfortable with this? Sort of? Kind of? What's the range of this function?
-1. It's less than 0. So it is less than x, which is less than 1.
X? Is it X that we're dealing with?
It's not. Theta?
No, the range is dealing with this axis.
Yeah.
So it's
Y.
Yeah,
Oh, okay.
yeah. And so yeah, range would be -1. Right? Do you know where we got these numbers? This is from the amplitude, plus or minus the amplitude. Okay? So we know that there's one up here and there's one down there. So that means that the whole graph is just going to be between those two values. You guys remember how to write this using the brackets, parentheses, and stuff?
Yeah.
How do we write that?
It's bracket -1, comma 1 bracket.
Yeah, exactly. Got it? So that's the range of this function. And yep, here to continue, just draw arrows. Cool, let's move on to cosine. Man, we're running out of time really fast. Okay. So, cosine x looks pretty much exactly like sine x, except that it's moved over a little bit. Cosine x looks like this. Right. Okay, notice that once again, it's still a wave function called sinusoidal. These kinds of waves are called sinusoidal. Instead of going through 0, 0, it has one of its peaks on the y-axis. Okay. And the general equation it's pretty much the same as sine. This is the amplitude. Okay, period is 2 pi over b. And these are just moving around. Pretty much the same thing. What I want you to notice is what if I graph. So this is what sine x looks like, right? This looks pretty much the same thing as that, right? These two graphs, except this one's moved over, right? So if I were to graph sine of x minus pi, well, let's do pi over 2 minus x. Pi 2 minus x. What does this look like? This is exactly the same as our cosine function. Okay? You guys see that? So this is going to be kind of pretty important when we start working with identities, which we're going to talk about sometime later in the week. Basically, sine of 2 pi minus x is the same thing as cosine x. Cosine of 2 pi minus x is the same thing as sine x. And this is just graphically showing you how that works. So when you're graphing cosine, it's pretty much exactly the same as what we've been doing for sine, except you're keeping track of sort of different points. You can use whatever points to keep track of as you want. I like to keep track of these two bottom ones and like treat this as my kind of middle point, so to speak. So like this is half your period from here to here, and this is half your period from here to there. Pretty much the same thing as sine, besides that. So let's just do some practice. Are you guys okay with this? Okay, cool. So, I'm sad. That equals 2 cosine 3x. Let's graph that.
Question. What makes this different from sine? How do we differentiate?
The difference is just that if you look here on this graph, instead of going through 0, 0, the parent function goes through 0, 1. Yeah, so the peak is at one of these halfway points. Essentially, the structure is the same as the sine graph, except it's shifted a little bit, just like I showed you with the other thing. So when you're graphing this, just keep track of, like, I would keep track of this point as your, like, central point or whatever, and then do essentially the same thing as you've been doing, like divide the period by 2.
Is it 0, 1 just in the case of cos x?
Cosine x?
Yeah. What is it? What is the origin point, like center?
This doesn't go through the origin,
Or not
so
origin, sorry, I meant like center point.
you can really take whatever point you want, but the one that I like to work with is right here because it's convenient because it goes right through this axis, and so if you move it left or right, you can keep track of where it's going. But really, it doesn't really matter which point you decide to keep track of. So, yeah. We're doing the same thing, finding the period and then dividing that by 2. And then dividing that by 2.
Does the 3x have any impact on that point, or is that point always just 0?
Oh, I see what you're saying. So, are you saying like cosine 3x?
Yeah. Okay. All right.
Does that answer your question? Yeah. Can you tell me why that would not affect that point?
Because it has no relation to like the actual equation.
It does, but when you're doing a horizontal, I'm not sure if Jimmy talked to you about this. I know I talked about it when I was doing Algebra, but when you guys are doing horizontal stretches or compressions, it's affecting the x coordinate of your point. And if this point's x coordinate is 0, no matter what you multiply 0 by, it's still going to be 0. So if you stretch this thing way out or compress it really far in, 0 times whatever is still 0. So that's why this point is not affected by that. You done?
I think so.
Cool. Can you tell me what the period is?
5.
Period's 5?
I think I did that one.
Okay.
Wait, so is it? Do you use 3 as your coefficient?
Yes.
Oh, okay. Yeah, that's
Yes.
right. So 2 pi over 3.
2 pi over 3. Okay.
And amplitude is 1.
Are you looking at the wrong thing? I think you're looking at the. That's okay. What is going on? What is going on? Oh no! How do I disable this stuff?
You just gotta. It's Facebook. Just.
Oh, if I just close Facebook?
Yeah, just close Facebook.
Okay. No, that's no.
You have to log out.
Oh really?
Yeah.
Oh great! I'll just do it later. Whatever.
I would. It doesn't.
Okay.
And we're just popping.
So amplitude is. Tristan?
2.
Good. Okay. So I'm gonna draw my 1, 2. Okay. Where should I draw? I'm gonna start right here. So my crest is going to be, like the peak of the graph is going to be on the y-axis, right? So that's the first point I can draw. And then how far this way should I go?
2 pi over 6.
Yeah, 2 pi over 6. So what does that simplify to?
1 pi over 3.
Yeah, pi over 3. And go here, pi over 3. Okay, and what's this way?
But if on the amplitude, oh wait, actually, that makes sense. Because I was thinking,
Did you answer your question? You're thinking.
No, when the amplitude is for sine, it's like when amplitude is 1, the origin is 0, right?
Yes, it
Okay.
starts.
Yeah, but
Right.
then when you do this one, it starts at 1. So shouldn't you add 2 to that?
Well, for this one, I'm starting here. The amplitude is just saying, so like if you have any kind of sine, cosine, whatever graph, the amplitude is just saying if you cut this like straight in half, directly in half, so there's like equal height on either side, what is this, right? So for this graph, we haven't moved it up or down at all, so we're still measuring the height from this axis. The only difference is that for cosine, the y-axis is right here, so it'll intersect at that point up there. And so this is going to be your amplitude, like this, because you go up to your amplitude. And with sine, it's different because,
Wait,
sorry, it's just terrible.
But then if the amplitude is 2, then it starts from 1, right? So that it adds 2 to 1.
No, it starts from, we're still going to be counting from the x-axis. Sorry. Even though this graph starts at 1 up here,
Yeah.
when we do a vertical stretch with this, that point is going to move up. It's not that we're adding 2 to that. We're just going 2 up from the x-axis and 2 down from this. If you were to slice it straight through,
So the
straight through right here.
amplitude is then measured from the x-axis.
If you haven't moved it, it's basically like I said before. This is your graph, and you slice it straight through the middle. It would be this distance. And so I'm not going to say it's from, in this case, yes, it's the distance from the x-axis, but if you were to go like +3 or something, now it's not from the x-axis, it's still from this middle line. Let's say y = 3. It's going to be the distance from this line up that way and the distance from there down that way. Okay, that's what the amplitude is saying. So if I said 3, see, it would just go farther from this line up and down. Get it? Cool. Okay. So, okay. So put it there. Okay, and we know that this graph is going to go through the x-axis at halfway through these points, right? Does that make sense? Kind of?
Yeah.
Critical points are always like a quarter of the way through. So what should I put here?
6.
Okay, what should I put here?
6.
Okay, so my points are going to be here, 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 and here. Okay, and then you just draw a curvy. Okay, there it is.
Now take a picture because
Yeah,
it's kind of messy now.
So for the sake of time, I've only been graphing one period. In general, you should extend your graph to include at least 2 periods because this is kind of unclear. Like this could be a quartic function or something like y = x⁴. You don't know. So they usually want you to do at least 2 periods so that it's pretty clear that you're drawing a sinusoidal function. But yeah. Okay, are we good with cosines? Do you want to do more practice or we move on? Actually, I'm making the decision. We're moving on because we're out of time. Okay. Tangent. Someone tell me what the ratio is for tangent. Tangent, in terms of tangent, what's tangent in terms of sine and cosine?
It's sine over and sine over cos.
Yeah.
Cosine.
tangent equals sine of tangent theta equals sine theta over cosine theta. Sine theta. Okay, so when are fractions undefined?
One they have like a 0, one they have.
Right, a 0 in the denominator, right? So tangent theta is going to be undefined and cosine theta equals 0. Okay, so whenever cosine theta equals 0, we're going to have a vertical asymptote because this is not possible. You can't divide by 0. Does this make sense? Okay, so that's why we're going to have asymptotes. Okay, so tangent of x is not the same as those sine and cosine things that we've been dealing with. It looks like this, and it has an asymptote periodically. So in this case, the asymptotes would be at pi over 2, and then at pi.
Are they only vertical?
Let's see. Yes, they're only vertical. Pi plus pi over 2, and then 2 pi. Okay, you see that? These are the asymptotes. And the reason for that is when x is pi over 2, if we look at a unit circle, x is pi over 2, that's 90 degrees. Okay? What is sine of x? If we look at a unit circle, can you see it? It's kind of hard to see. I only have one copy of this, but someone can use that too. You're too far away. Can you see it? Not really. Use that. You guys can share it with me. So what is sine of pi over 2? Harrison?
Sine.
It's root 3 over 2.
No, I'm looking at the right point. So pi over 2 is right here. It's 90 degrees right there.
Oh.
Okay, and sine is going to be the y-coordinate. So 1. Okay, and what's cosine? Cosine is the x-coordinate.
0.
Right. So at 90 degrees at pi over 2, and theta equals pi over 2, then tangent of theta is sine over cosine, which is 1 over 0. Is that okay? No, we can't do that, right? So that's why we're going to have an asymptote there. So pi over 2, an asymptote. I'll talk about it in a second. So for tangent, the parent function of tangent x, one period is just pi instead of 2 pi. If we have time, I would go over the unit circle and why that is so, but we don't really have time. I'm trying to finish tangent like really, really fast. So all you need to know is that period is instead of 2 pi over b, it's not that. That's for sine and cosine. Okay? For tangent and cotangent, it's pi over b. Okay? You see that? Okay, so essentially our asymptotes, we can treat them kind of as like the things that break up each period and separate them.
They don't look like they have this separation. Like,
Yeah,
it
they
doesn't
don't-
look like they're connected.
They're not connected, yeah, that's right. This is a discontinuous, it's not continuous. So that means every pi is going to be another asymptote. So this would be negative pi over 2, right? And then if we continue on this way, this would be negative 3 pi over 2. Are you following? Every pi is another asymptote. Okay? And for tangent, it goes straight through the origin and goes upwards like that. Almost looks like a cubic function. Almost. Okay? That's terrible. It's like screaming in agony. Okay. So, so if we were to write the general formula as y equals a tangent of bx plus c plus d. So there's no amplitude for the tan function because it just stretches on forever. But A still does represent vertical stretches. So if you were to graph like 2 tangent of x, you should probably make it clear that it's like steeper because it's stretching it vertically. Make sense? And one point that people tend to watch out for is, let's see if I can do this, pi over 4, 1. There we go. Okay, so in tangent, let's just draw the parent function right here. So a few notable points about this function is that halfway on either side of this origin point, this is pi 4, and this is pi 4. This right here is going to be 1 at pi over 4 halfway through, and then on the other side it's -1. Okay, so if you were to draw the parent function, it would look like this. Now, if you were to vertically stretch it, this point initially was pi over 4, 1. If you made it 2 times tangent of x, what would this point change to? Person? We're doing a vertical stretch, so we're only dealing with the y value.
So, out for 2.
Yep, exactly. So this would just get moved up to 2. And you go up there. And go down there. So then your newer function would look like that. Right? When you're moving it left, right, up, down, this is once again a good central point to kind of keep track of and move it around places. And we're out of time. That's it. So there's a tangent function practice thing on your homework that you guys should try. There are a lot of problems on that homework. Most of them should be pretty straightforward, and you can do them really fast. If you have problems with any of them, you can come to office hours, or just skip it and we'll go over it in class next time. And there is some stuff that we have not covered, so just hold on 1 second while I go over what stuff you need to pay attention to. So number 16 you can ignore. We'll do that next time. 15b you can ignore because we haven't dealt with cosecant yet. Erin, what was it that you had to correct?
For numbers 5 through 10, I know it's assigned 2 coterminal angles, but for some of them there are only 1. I believe they should be number 6, 9, and 10. So for those, there's only 1 coterminal angle, so just put 1 of them. And we didn't really go over how to find the coordinates if you're given an angle and a radius, because we didn't really do the unit circle today. So maybe skip that and we'll go over unit circle during the next class, and then you can do it then.
Okay, sounds good. And I think on the homework for the graphing ones, I said state whether it's an odd or even function. You can ignore that part too because we didn't go over that. Okay? Sorry, there's a lot of changes. It is plugged in.
No, it's plugged in. It shows like.
Oh, that one. Oh. All right, thanks, guys.
Quick save.
I didn't know there were different degrees of save.
Like, oh no, half save. Oh no, quarter save. Well, that's actually possible. Alright,
Aaron 10. You know what sucks about whiteboards?
you have to wipe them.
No, not that.
Your fingers.
My nose!
Why your nose?
My poor nose!
Why your nose?
Oh, great. I think the thing is still recording. I think it caught that nose thing. Hello, guys. If any of you are watching from home, I apologize for our weirdness, but that's part of the job description because we're